What if you fell into the ocean of Europa? Imagine this. You're falling. Not through air, not through water as you know it, but through absolute darkness toward an alien ocean that has never seen a single ray of sunlight. Above you, kilometers of ancient ice seal you off from the universe. Below you, a lightless abyss extends deeper than Mount Everest is tall, filled with water that has existed in isolation for potentially billions of years. This is not Earth. This is Europa, Jupiter's mysterious moon, and you're about to discover what lies beneath its frozen surface in the most visceral way possible. The pressure builds around you with every meter you descend. Your lights, if you have any, penetrate only a few meters into the ink-black void. And then you begin to wonder, in all this darkness, in all this crushing emptiness, are you truly alone? What if something down here has been waiting, evolving, adapting to conditions so extreme that life as we understand it shouldn't exist at all? What if you're not the first thing to fall into this ocean, but simply the first thing conscious enough to realize the horror and wonder of where you are? Let's step back for a moment. Before we can understand what would happen if you fell into Europa's ocean, we need to understand what Europa actually is, and why this small moon, barely larger than our own moon, has captured the imagination of scientists and dreamers alike. Europa is the fourth largest moon of Jupiter, discovered on January 8, 1610, by Galileo Galilei, along with three other moons that would forever change our understanding of our place in the cosmos. When Galileo pointed his primitive telescope at Jupiter and saw these moons orbiting the giant planet, he provided the first observational evidence that not everything in the universe revolved around Earth. But Galileo could never have imagined what Europa truly was. To him, it was just a point of light dancing around Jupiter. To us, 4 centuries later, it represents one of the most promising places in our entire solar system to find extraterrestrial life. Europa is small by planetary standards, with a diameter of approximately 3,122 kilometers, just slightly smaller than our moon. But size is deceiving. What makes Europa extraordinary isn't its dimensions, but what lies beneath its surface. The entire moon is covered in a shell of water ice, not the pristine white ice you might imagine, but ice that has been tortured and transformed by immense forces. From space, Europa appears as a pale, cream-colored sphere, crisscrossed with reddish-brown streaks and cracks that create patterns resembling the veins in a bloodshot eye. These aren't just simple cracks. They're enormous fractures in the ice, some stretching thousands of kilometers, evidence of the tremendous geological activity occurring on this frozen world. The surface temperature on Europa averages around -160 degrees Celsius at the equator and drops to -220 degrees Celsius at the poles. This is cold beyond anything you've likely experienced. Cold enough that carbon dioxide doesn't just freeze, it becomes as hard as rock. On this alien landscape, there is no atmosphere to speak of, just a tenuous envelope of oxygen so thin it barely qualifies as an exosphere. The oxygen isn't there for breathing, though. It's created when Jupiter's intense radiation bombards the ice surface, splitting water molecules apart. Speaking of radiation, Europa orbits well within Jupiter's powerful magnetosphere, meaning the surface is constantly bathed in radiation levels that would kill a human being in a matter of days. The radiation dosage on Europa's surface is approximately 5.4 sieverts per day. To put that in perspective, a dose of 5 sieverts all at once would likely be fatal to a human. On Europa, you'd receive that every single day. But beneath that irradiated, frozen surface lies something remarkable. Scientists are now virtually certain that Europa harbors a global ocean of liquid water beneath its ice shell. This isn't speculation or wild theory. Multiple lines of evidence point to this conclusion. The Galileo spacecraft, which orbited Jupiter from 1995 to 2003, gathered data showing that Europa has an induced magnetic field, something that could be explained by a salty, electrically conductive fluid beneath the surface. The moon's surface features, those strange cracks and ridges, suggest that the ice shell is floating on something liquid, constantly being fractured and reformed by tidal forces. Even the way Europa wobbles slightly as it orbits Jupiter something scientists call libration, indicates that the ice shell isn't locked to the rocky interior, but rather separated from it by a liquid layer. How deep is this ocean? Conservative estimates suggest the ice shell above the ocean is between 15 to 25 kilometers thick, though some models propose it could be as thin as 10 kilometers in some places or as thick as 30 kilometers in others. Beneath this ice, the ocean itself is estimated to be between 60 to 150 kilometers deep. Think about that for a moment. The deepest point in Earth's oceans, the Challenger Deep in the Mariana Trench, is about 11 kilometers down. Europa's ocean could be more than 10 times deeper. In fact, despite being smaller than our moon, Europa may contain 2 to 3 times more liquid water than all of Earth's oceans combined. Every drop of that water has been sealed away from the sun, isolated in complete darkness, possibly for the entire 4.5 billion-year history of the solar system. What would that water be like? We have strong reasons to believe it's salty, probably similar to Earth's oceans in salinity, perhaps even saltier. The reddish-brown material we see in Europa's cracks and geological features might be salts and other minerals that have welled up from the ocean below, been altered by radiation, and stained the ice. Spectroscopic analysis suggests these discolorations might include magnesium sulfate salts, similar to Epsom salt, as well as sulfuric acid and other compounds. Some of the darker reddish materials might even be organic compounds, though that remains uncertain. The presence of salts is crucial because it would lower the freezing point of water, helping to keep the ocean liquid. But the primary heat source keeping Europa's ocean from freezing isn't the distant sun, which provides barely 1/25 the warmth Europa would receive if it orbited near Earth. Instead, Europa stays warm through tidal heating. Tidal heating is one of the most fascinating phenomena in planetary science. Europa orbits Jupiter in an elliptical path, getting closer and farther from the giant planet over the course of each 3.5-day orbit. Jupiter's immense gravity, more than 300 times Earth's mass concentrated in one place, pulls on Europa with varying strength depending on how close the Moon is. This constantly squeezes and stretches Europa's interior, flexing it like a rubber ball you squeeze in your hand. That flexing generates friction, and friction generates heat. The same process heats another of Jupiter's moons, Io, so effectively that it's the most volcanically active body in the solar system. On Europa, the heating is less extreme, but enough to melt and maintain a vast ocean beneath the ice. The ocean might even have volcanic vents on its floor, similar to the hydrothermal vents on Earth's ocean floors, where superheated mineral-rich water spews from cracks in the crust. On Earth, these vents support entire ecosystems that don't rely on sunlight, but on chemical energy. Could the same be true on Europa? Now, let's imagine the scenario. You're going to fall into Europa's ocean. How did you get here? This isn't a journey you make by accident. Europa orbits Jupiter at a distance of approximately 671,000 kilometers from the planet's center, and Jupiter itself is, at its closest, around 628 million kilometers from Earth, though that distance varies enormously depending on where Earth and Jupiter are in their respective orbits. Even at light speed, it would take between 33 and 52 minutes for a signal to travel between Earth and Europa. With current technology, a spacecraft takes years to make the journey. The Galileo probe took 6 years, using gravitational assists from Venus and Earth to slingshot its way to Jupiter. Future missions might be faster, but you're still looking at a multi-year voyage through the solar system. Arriving at Europa would be dangerous. The radiation environment is so hostile that any spacecraft needs significant shielding. Humans would need protection that current technology struggles to provide. Let's say, for the sake of our thought experiment, that you've arrived on the surface in some kind of protected lander. You're standing on ice that could be anywhere from 10 to 30 kilometers thick, ice that's been fractured and refrozen countless times, creating a landscape of ridges, cracks called lineae, and strange circular features called lenticulae, which might be places where warmer ice has welled up from below. The ice beneath your feet is harder than concrete at these temperatures. The horizon is close, much closer than on Earth, because Europa's smaller size gives it a tighter curve. If you could see through the radiation and the faint atmospheric haze, you'd see Jupiter dominating the sky, an enormous sphere more than 24 times larger in apparent size than our moon appears from Earth, swirling with storms and bands of clouds, a monster planet that would be simultaneously beautiful and terrifying. Your mission, impossible as it sounds, is to reach the ocean. How do you get through 15 or 20 kilometers of ice? On Earth, we've drilled into ice sheets in Antarctica and Greenland, but nothing close to this thickness, and certainly not in temperatures this extreme or under these conditions. Various concepts have been proposed: thermal probes that melt their way down, nuclear-powered cryobots, even explosives to crack through the ice. Let's imagine you have access to some advanced boring device, something that can melt and drill through the ice. The descent begins. At first, you're moving through surface ice that's been heavily processed by radiation, mixed with those strange salts and possibly organic compounds. The ice here is chaotic in some places, broken and refrozen into jagged formations. As you descend, the ice becomes clearer, less contaminated by surface materials. The temperature, paradoxically, begins to rise, though rise is relative when you're starting at minus 160 Celsius. With every kilometer you descend, the pressure increases. The weight of all that ice above you is immense. At 15 kilometers deep, the pressure would be roughly 1,500 times Earth's atmospheric pressure at sea level, comparable to being 1.5 kilometers deep in Earth's ocean. Your descent vehicle needs to withstand this, and the pressure will only get worse. You might descend for hours or even days, depending on your method and speed. Imagine the claustrophobia of it, burrowing through endless ice, no natural light, just the artificial illumination of your vehicle and the endless frozen walls sliding past. Would the ice be clear enough to see through, or would it be cloudy, filled with bubbles and impurities? We don't know. Scientists have speculated that the ice might be relatively clear in some regions, clouded in others. You might pass through different layers, each with its own characteristics, each formed during different periods of Europa's geological history. The ice isn't static. Convection might occur, with warmer ice rising from below and colder ice sinking, creating a slow churning motion over geological timescales. You could be passing through ice that last saw the surface 10 million years ago, or ice that formed last week in geological terms. Then, after what feels like an eternity of descent, something changes. Your instruments detect a change in the ice structure. It's becoming slushier, less solid. You're approaching the bottom of the ice shell, the transition zone between solid ice and liquid water. This boundary might not be sharp. There could be a gradual transition, a zone of mushy, partially melted ice several meters or even kilometers thick. Or perhaps the boundary is sudden, a relatively sharp interface between ice and ocean. Either way, you're about to break through. And then it happens. Your vehicle punches through the final layer, and suddenly you're falling into liquid water. After descending through kilometers of solid ice, the sensation of falling through fluid would be jarring, alien. But this isn't water as you know it. You've just entered an ocean that has been completely isolated from the sun for potentially billions of years. The water is pitch black, darker than the deepest caves on Earth, darker than the midnight zone of Earth's oceans. On Earth, even in the deepest ocean trenches, there was once light at the surface, and organisms evolved from ancestors that knew sunlight. Here, there has never been light except perhaps the faint glow of bioluminescence, if life exists and if it evolved the ability to produce light. But you're descending into an abyss with no guarantee that anything living has ever existed here. The temperature of the water is shocking in its own way. It's not frozen, obviously, but it's hovering just barely above the freezing point, perhaps around minus 2 degrees Celsius at the top of the ocean, thanks to the salts dissolved in the water lowering its freezing point. As you descend deeper, the temperature might rise slightly, heated from below by whatever warmth emanates from Europa's rocky core and any hydrothermal activity. But you're never going to encounter what humans would consider warm water. This is a cold that would kill you in minutes if you were exposed to it without protection. In water this cold, your body would lose heat rapidly, 25 times faster than in air of the same temperature. Hypothermia would set in within minutes. Your muscles would stop responding. Your consciousness would fade. Death would follow shortly after. But let's say you're in a protected vessel, something that can withstand the pressure and maintain a livable environment inside. You begin your descent into the ocean proper. Above you, the ice ceiling is invisible in the darkness. Below you, the abyss awaits. If you have lights, they penetrate only a few meters into the water. The water might be clear, or it might be filled with particles, suspended sediments or organic matter if any exists, dead cells or minerals that precipitated out of solution. Every meter you descend increases the pressure around your vessel. By the time you've descended just 1 kilometer into the ocean, you're experiencing pressures around 1,400 atmospheres, similar to some of the deepest reaches of Earth's oceans. But you potentially have another 60, 80, even 150 kilometers to go. What would you see? In the beams of your lights, perhaps nothing at first. Just water, perhaps some particles drifting past. But consider this, if life exists on Europa, this is where it would be. Not on the irradiated surface, not in the ice, but here in the liquid ocean where water is available, where chemistry can happen, where nutrients might be available. Would you see movement in the darkness? Something swimming past, just at the edge of your lights? The imagination runs wild in an environment like this. Every shadow becomes potentially significant. Every flicker of movement could be life, or could be nothing more than a current or a particle catching the light. Let's talk about what you might actually encounter, based on what we know about life in extreme environments on Earth. Life exists in places we once thought impossible. The deep ocean vents on Earth, where water superheated to 400 degrees Celsius erupts from cracks in the ocean floor, support communities of bacteria, tube worms, shrimp, and other organisms that thrive on chemical energy rather than sunlight. These ecosystems run on chemosynthesis, where organisms convert chemicals like hydrogen sulfide into energy. If Europa has similar vents on its ocean floor, similar ecosystems could theoretically exist. But would they look anything like Earth life? This is one of the great unknowns. Life on Earth all shares a common ancestor and uses the same basic biochemistry. DNA, RNA, proteins made from amino acids, cells with lipid membranes. If life arose independently on Europa, it might use completely different chemistry. It might not even be carbon-based, though carbon's unique properties make it the best element for complex chemistry. It might use different solvents, different information storage molecules, different energy sources. Or it might be remarkably similar to Earth life, if the laws of chemistry and biology constrain life to certain forms. Some scientists speculate that if life exists on Europa, it's probably microbial, similar to bacteria or archaea on Earth. The ocean might be filled with microscopic organisms, too small to see with the naked eye, but present in quantities that would make the ocean a kind of thin, living soup. Others have speculated about more complex life. Could larger organisms exist? On Earth, the deep ocean supports not just microbes but also complex animals. Fish, squid, crustaceans, worms. These creatures ultimately depend on a food chain that traces back to the surface, where sunlight drives photosynthesis. Europa has no such connection. Any complex life would have to depend entirely on chemical energy from the ocean floor or from chemical reactions in the ocean itself. This would likely limit the amount of energy available and thus limit the size and complexity of organisms. Most scientists think that if life exists on Europa, it's probably simple and sparse, but nobody knows for certain. That's what makes it so tantalizing. Imagine, as you descend, your instruments detect something. A chemical signature that doesn't match non-biological processes. Perhaps an unusual concentration of organic molecules, or isotopic ratios that suggest biological activity. Your heart races. You slow your descent, trying to locate the source. Is it coming from the water itself, or from somewhere deeper? You continue down, the pressure now building to levels that would crush almost anything from Earth's surface. 10 kilometers deep into the ocean, you're at pressures exceeding 10,000 atmospheres. The water around you, if it contains any gases, would be compressed to extraordinary densities. Your vessel's hull creaks and groans under the stress. Every seal, every joint is tested beyond normal limits. At these pressures, water itself behaves strangely. It becomes more viscous, thicker, though still liquid. The speed of sound in water increases with pressure, so sound travels faster here than at the surface. If there were any sounds, any biological noises or geological rumblings, they would propagate through the water in ways different from Earth's oceans. You might hear clicks, groans, pings, the sounds of ice shifting kilometers above you, or the rumble of geological activity far below. Or you might hear nothing at all except the hum of your own equipment, making the silence even more oppressive. As you go deeper, you wonder about the age of this water. On Earth, ocean water is constantly cycled through evaporation, precipitation, mixing. Europa's ocean has no such cycle. The water here might be ancient beyond comprehension, individual molecules that have been trapped beneath the ice for billions of years. Or perhaps there's more circulation than we think. Maybe water is cycled through the ice shell somehow, perhaps through cracks that penetrate all the way through, allowing ocean water to well up and freeze at the surface while surface ice melts at the bottom. Some of Europa's surface features, those strange circular lenticulae, might be places where this happens. If so, the ocean might be less isolated than we think, with at least some exchange with the surface, though any such exchange would be incredibly slow by human standards. 20 kilometers deep. 30 kilometers. The pressure is now approaching 30,000 atmospheres or more. You're deeper than any ocean on Earth. At these pressures, even the chemical structure of water might be affected. Under extreme pressure, water can form exotic ice phases that exist even at higher temperatures. Could there be strange layers in this ocean where pressure-induced ice formations exist, creating a sort of underwater ice layer? We don't know. The physics of water at these extreme pressures and low temperatures is still being studied. And then, after descending for what might be hours or even days depending on your rate of descent, your sensors detect something solid below. You're approaching the ocean floor. This is the rocky layer of Europa, the silicate core that lies beneath all that ice and water. What would this floor look like? On Earth, the ocean floor is varied. Flat abyssal plains covered in sediment, mid-ocean ridges where new crust is formed, deep trenches, underwater mountains. Europa's ocean floor is a complete mystery. It could be relatively smooth, covered in fine sediments that have settled out of the water over billions of years. Or it could be geologically active, with volcanic vents, cracks, fissures, perhaps even underwater volcanoes if there's enough heat from tidal flexing of the rocky core. This is where life, if it exists, would most likely be concentrated. On Earth, the deep ocean vents support the highest concentration of life in the deep sea. If Europa has similar features, they would be biological hotspots, places where chemicals from the interior meet the ocean, providing energy for microbes to harvest. You direct your descent toward the floor, your lights finally illuminating something other than empty water. The floor materializes in your lights, and you see. What do you see? We can only speculate. Perhaps a flat plain of fine, dark sediment, undisturbed for eons. Perhaps rocky outcrops, basaltic formations similar to Earth's ocean floor. Perhaps, if you're lucky or unlucky depending on your perspective, something more active. A vent, spewing dark, mineral-rich water into the surrounding ocean, creating a plume that rises like smoke. Around such vents on Earth, you'd find tube worms, bacteria mats, crustaceans. Here, would you find anything similar? Or would the area be barren, lifeless despite the available energy. Let's imagine the most exciting possibility. As your lights play across the vent, you see something. Movement. Structures that don't look purely geological. Mats of something coating the rocks. Perhaps microbial films similar to those on Earth. And then, something larger. Could it be a shape, perhaps cylindrical, perhaps articulated, moving slowly in the water near the vent? Your mind struggles to process it. Is it alive? Is it some kind of organism, or just a geological formation that happens to look biological? You move closer, every sensor recording, every camera focused. This is the moment that would change everything. The discovery of extraterrestrial life, even simple life, would be the most profound discovery in human history. It would answer the age-old question, are we alone? It would provide a second example of biology, allowing us to understand what features of life are universal and what are accidents of Earth's particular history. If life arose independently on Europa, it would suggest that life is common in the universe, that wherever conditions permit, life finds a way. The implications would be staggering, philosophical, theological, scientific. But let's return to the brutal reality of your situation. You're not just an observer here. You're a human, or at least you were, in a protective vessel at the bottom of an alien ocean. Even with the best technology we can imagine, this is a one-way trip. The energy required to ascend through hundreds of kilometers of water, then bore back through the ice shell, then launch from Europa's surface to return to Earth, is prohibitive. You're here to explore, to discover, to send data back to Earth or to a relay satellite, but you're not going home. As you explore the ocean floor, moving along it, mapping, sampling, analyzing, you have time to contemplate your situation. Above you, 100 kilometers of water and 20 kilometers of ice separate you from space. The pressure at this depth is crushing, perhaps 50,000 atmospheres or more at the deepest parts of the ocean. Your vessel, however well designed, is being tested to its absolute limits. Any failure, any crack, any seal that gives way, would be catastrophic and instantaneous. The water would rush in with such force and speed that you wouldn't even have time to perceive what's happening. The pressure would crush you before your nerves could transmit the sensation to your brain. But let's say your vessel holds. You continue exploring. You collect samples of the water, the sediments, perhaps even samples of the potential biological materials. Your instruments analyze the chemistry. What would Europa's ocean water taste like if you could taste it? Salty, certainly. Perhaps bitter from dissolved minerals. The water chemistry would tell us about Europa's history. The ratios of different isotopes of hydrogen and oxygen could tell us where the water came from, whether it's original to Europa's formation or was delivered by comets. The dissolved minerals could tell us about the composition of Europa's interior and what kind of rock-water interactions are occurring. If you found organic molecules, that would be extraordinary even without finding life. Organic molecules, the carbon-based compounds that are the building blocks of life, can form through non-biological processes. We've found them in meteorites, in comets, in the atmospheres of planets and moons. But finding complex organic molecules in Europa's ocean would suggest interesting chemistry is happening. Chemistry that could potentially lead to life even if it hasn't yet. The presence of certain molecules, like amino acids in particular ratios, or long-chain carbon molecules, or nucleotides similar to those in DNA and RNA, would be smoking guns for biology. What about the physical sensations of being here? Even inside your vessel, you'd feel different. Europa's gravity is only about 13% of Earth's, similar to our moon. Things would feel lighter, movements would be easier, but also stranger. The combination of weak gravity and enormous pressure would create a unique environment. Water would still be denser than you, so you'd still sink without propulsion, but everything would have a strange, dreamlike quality to it. If you could somehow survive outside the vessel, which you absolutely couldn't, swimming would feel different, the water responding differently to your movements in the low gravity. Time would feel distorted as well, though not due to relativity. The isolation, the unchanging darkness, the lack of any day-night cycle, would play havoc with your circadian rhythms. On Europa, a day is the same as its orbital period, 3.55 Earth days, but beneath the ice and ocean, you'd never know it. There's no sun to rise and set, no external cue to tell you what time it is. You'd be living by artificial time, whatever schedule you or your equipment maintained. The psychological effects of this would be profound. Humans evolved for cycles of light and dark, for the rhythms of Earth. Here, in eternal darkness, your mind would be in alien territory as surely as your body. Consider the sounds. Water is an excellent conductor of sound, much better than air. Any sounds would travel far and fast. If Europa's ocean has geological activity, you might hear it, the rumble and crack of ice shifting above, the groans of Europa's rocky interior flexing under tidal forces, the hiss and roar of hydrothermal vents if they exist. If life exists and is active enough, you might even hear biological sounds. On Earth, the ocean is filled with the sounds of life. Whale songs, dolphin clicks, the snapping of shrimp, the sounds of fish. Would Europa's ocean have its own soundscape, or would it be eerily silent except for geological noises? And what of the ice ceiling so far above? Is it completely solid, or are there pockets, caverns, voids within the ice? On Earth, ice sheets can have complex internal structures. Europa's ice shell, subjected to tidal flexing and heating from below, might have regions where the ice is partially melted, creating chambers filled with liquid water within the ice itself. These could be isolated pockets, or they could connect to the ocean below. Some scientists have speculated that life might even exist in these ice chambers, protected from radiation by the ice above, but potentially receiving some filtered light if they're close enough to the surface, and having access to ice and perhaps nutrients. These would be unique environments, unlike anything on Earth. Let's talk about what would happen to an unprotected human body if it were somehow exposed to Europa's ocean. We've discussed the cold and the pressure, but let's be more specific. If you were suddenly exposed at the ocean floor, the pressure would kill you essentially instantly. At 50,000 atmospheres, your body would be compressed catastrophically. Air spaces, your lungs, sinuses, ears, would collapse immediately. Your tissues, made mostly of water, would be compressed slightly, but the pressure differential would cause immediate and catastrophic damage. Blood vessels would rupture, organs would fail, bones might even crack. You would not drown because you'd be dead before any water could enter your lungs. If you were exposed near the surface of the ocean, where pressures are only a few thousand atmospheres, the death would still be rapid but slightly different. The cold would be more immediately relevant. In water at -2 Celsius, you'd lose consciousness within minutes from hypothermia. The mammalian diving reflex would kick in, slowing your heart rate and redirecting blood to your core, but this adaptation evolved for diving in relatively shallow, relatively warm water, not for the abyss of Europa. Your blood would thicken slightly in the cold, making your heart work harder at the very moment it's slowing down. Ice crystals might begin forming in your extremities. Your muscles would stop responding. The pressure would still be crushing your lungs and damaging your body, but you'd likely be unconscious from cold and lack of oxygen before the pressure damage became the primary killer. There's something deeply unsettling about imagining death in such an alien place. On Earth, even in the most remote locations, your body would eventually be found, or it would decompose through the action of bacteria and scavengers, returning your molecules to the ecosystem. On Europa, what would happen to a human body? If life exists, would it consume you, breaking down your organic molecules for energy and nutrients? Or would you be made of such alien biochemistry from the perspective of Europan life that you'd be inedible, your body preserved indefinitely in the cold water, a monument to human exploration? The pressure might mummify you in a sense, compressing your tissues into a distorted version of your former shape. Or perhaps chemical processes in the water would dissolve you over time, breaking down your complex molecules into simpler compounds that would disperse into the ocean. These are grim thoughts, but they highlight just how alien Europa truly is. This isn't a place for humans. It's a place that would kill us in countless ways if we weren't protected by layers of advanced technology. And yet, the lure of discovery is so strong that we dream of going there anyway, of sending our robots if not ourselves, of piercing that ice shell and exploring that ocean. Let's discuss what we're actually planning to do. NASA's Europa Clipper mission, scheduled to launch in October 2024, will perform dozens of flybys of Europa, studying its ice shell, its ocean, and its geology in unprecedented detail. It won't land, and it certainly won't drill through the ice, but it will map the surface, analyze the ice composition, measure the thickness of the ice shell more precisely, and study the ocean's characteristics using magnetic field measurements and other techniques. The European Space Agency's JUICE mission, the Jupiter Icy Moons Explorer, launched in April 2023, will also study Europa along with Ganymede and Callisto. These missions will provide crucial data for planning any future landing mission. A lander mission has been proposed. It would touch down on Europa's surface, analyze the ice and any materials on the surface, and perhaps even drill a short distance into the ice to collect samples that haven't been as heavily processed by radiation. This would be extraordinarily valuable, but it's just the beginning. The real prize would be a mission that actually reaches the ocean. Various concepts have been studied. A cryobot that melts through the ice, a submarine that explores the ocean, a combination of systems. The technical challenges are immense. How do you power a mission through tens of kilometers of ice and then through an ocean? Nuclear power seems like the only viable option. How do you communicate back to Earth through all that ice and water? You'd need relay systems, perhaps a series of transponders left in the ice during descent. How do you navigate in a completely dark, unmapped ocean? Sonar and other sensing technologies would be crucial. And then there's planetary protection. This is a critical issue that scientists take very seriously. If we send a probe to Europa, we need to be absolutely certain we're not contaminating the ocean with Earth life. Microbes from Earth, carried on a spacecraft, could potentially survive and even thrive in Europa's ocean if conditions are suitable. This would be a disaster for science because we could never be certain if any life we discovered was native or if it came from Earth. It would also be an ethical catastrophe, potentially damaging or destroying a native ecosystem. Spacecraft destined for Europa need to be sterilized to an extreme degree, far beyond what's required for missions to other destinations. Even with the best sterilization, it's nearly impossible to guarantee complete sterility. Some scientists argue we shouldn't go to Europa at all until we're absolutely certain we can do so without risk of contamination. But the drive to explore is powerful. Humans have always pushed into unknown territories, often despite enormous risks and costs. Europa represents a new kind of frontier, not just unexplored but fundamentally different from anywhere humans have ever been. If life exists there, it would be life that evolved completely independently from Earth, in isolation, under conditions we're only beginning to understand. Studying such life would teach us more about biology, chemistry, and the nature of life itself than almost any other discovery we could make. What if the discovery changes everything we thought we knew? What if life on Europa turns out to be abundant, complex, even intelligent in some way? This seems unlikely given the energy constraints, but imagine if we were wrong. Imagine if the ocean teems with life, if there are entire ecosystems we can't yet imagine, adapted to the darkness and pressure in ways that would astonish us. Some science fiction writers have speculated about intelligent life on Europa, civilizations that evolved in the ocean and never knew the stars existed because they're sealed beneath kilometers of ice. In reality, the energy available from chemical sources almost certainly couldn't support large, complex, intelligent life. Intelligence is expensive metabolically. Human brains consume about 20% of our caloric intake despite being only 2% of our body mass. An intelligent organism needs abundant energy, which on Earth ultimately comes from the sun. Europa has no such energy source. But what if there are other energy sources we don't know about? What if Europa's interior is more geologically active than we think, providing more heat, more chemical energy? What if the ocean has concentrations of radioactive elements that decay and provide heat? What if there are processes we haven't even imagined? The universe has surprised us before. Black holes, dark matter, dark energy, quantum entanglement, all of these were unknown or seemed impossible until we discovered them. Could Europa hold similar surprises? Let's consider the philosophical implications of discovering life on Europa, even simple life. For all of human history, we've only known one example of life, Earth life. Every organism ever studied, from bacteria to blue whales, shares common ancestry and common biochemistry. This gives us a sample size of one when we try to understand what life is and how it works. Is DNA the only way to store genetic information? Are proteins the only way to build biological structures? Is water the only suitable solvent for life's chemistry? With only Earth to study, we can't answer these questions with certainty. We can theorize, but we can't know. A second example of life, from Europa or anywhere else, would change that. If Europan life uses DNA and proteins like Earth life, it would suggest that these are universal solutions to the problems of biology, that chemistry constrains life to certain forms. If Europan life uses completely different molecules and mechanisms, it would prove that life is more diverse than we imagined, that there are multiple ways to be alive. Either finding would be profound. And if we found life on Europa, it would also inform our estimates of how common life is in the universe. Currently, we don't know if life is an inevitable consequence of the right conditions, arising quickly and commonly, or if it's an extremely rare fluke that might have happened only once or twice in the entire universe. Finding life on Europa, in our own solar system, would strongly suggest that life is common. If it arose independently on two bodies in one small solar system, it probably exists on countless worlds throughout the galaxy. Think about what that would mean. For millennia, humans have asked, are we alone? It's one of the deepest questions we can ask. Finding even simple life on Europa would answer that question with a resounding no. We are not alone. Life exists elsewhere. And if life exists on Europa, a frozen moon with no direct sunlight and extreme conditions, then it likely exists on many of the billions of planets and moons in our galaxy. Some of that life might be complex. Some might be intelligent. Some might be far more advanced than us. The discovery of microbial life on Europa could be the first step in realizing that the universe is full of life, that Earth is not unique, that intelligence and consciousness might be common features of the cosmos. Or it could tell us something darker. What if we find evidence that life once existed on Europa but is now extinct? What if we find organic molecules, complex chemistry, perhaps even fossil-like structures, but no living organisms? This would suggest that life can arise but also fail, that extinction is a common fate. It would be a sobering reminder of our own fragility. If life on Europa died out, what killed it? A change in the ocean chemistry? A loss of heat from the interior? A catastrophic impact? Whatever killed Europan life, if it existed and is now gone, could potentially happen to Earth life as well. There's another possibility that's even stranger. What if life on Europa and life on Earth aren't independent origins but are related? This concept is called panspermia. The idea is that life could travel between worlds on meteorites. We know that rocks are blasted off planetary surfaces by impacts and can travel through space. Meteorites from Mars have been found on Earth. Could a meteorite from Earth reach Europa, or vice versa? It seems unlikely because Europa is so far away, and the journey would take so long that any organisms would likely be killed by radiation and vacuum. But some bacteria can form spores that are extremely resistant to harsh conditions. If life originated on one world and spread to another, then finding life on Europa that's biochemically similar to Earth life wouldn't prove that life is common, only that it can spread. How would we tell the difference? If European life uses the same genetic code as Earth life, the same 20 amino acids, the same cellular structures, it would be suspicious. The genetic code is somewhat arbitrary. There are many possible ways to map nucleotide triplets to amino acids, but Earth life uses one particular mapping. If European life used the same mapping, it would suggest common ancestry. If it used a different code, or different amino acids, or no genetic code at all, it would strongly suggest independent origin. These are the kinds of details that would matter enormously in interpreting any discovery. Let's return to your situation at the bottom of Europa's ocean. You've been exploring for days or weeks now. Your power supply is dwindling. Your life support has a limited capacity. You've made discoveries, collected data, perhaps even found evidence of life. All of this has been transmitted back to Earth, a signal that takes nearly an hour to arrive even at light speed, depending on where Earth and Jupiter are in their orbits. By the time anyone on Earth knows what you've discovered, you're already moving on to the next discovery. You're alone in a way no human has ever been alone, separated from your entire species by hundreds of millions of kilometers and by an ocean and ice shell that might as well be impenetrable. Do you feel fear, awe, loneliness, wonder? Probably all of these. The human mind wasn't designed for this kind of isolation and alienness. You might find yourself talking to yourself, narrating your experiences, anything to maintain some sense of human presence. Or you might fall into silence, letting the enormity of your situation wash over you. You're exploring a world that has existed in darkness for billions of years. Every sample you take, every measurement you make, every image you capture is revealing secrets that have never been seen by any conscious mind, as far as we know. And then, perhaps, your equipment begins to fail. The pressure has been relentless, finding tiny flaws and exploiting them. A seal begins to weep, letting in tiny amounts of water. Your power supply is running low. You've done what you came to do, discovered what you could, but your time is running out. What do you think about in these final hours? Do you think about Earth, about the people you left behind, about the sun you'll never see again? Do you think about what you've discovered, about the potential life you found, about how your discoveries will change humanity's understanding of the universe? Do you rage against the dying of the light, or do you accept it with equanimity? The water begins to seep in faster. Your instruments start failing one by one. The pressure is winning. You send one final transmission, a summary of everything you've learned, a goodbye, a message to the future explorers who might follow. And then, the pressure becomes too much. The vessel's hull fails catastrophically. The water rushes in, and in a fraction of a second, everything goes dark. Your consciousness ends, but your mission doesn't. The data you've sent back will be studied for generations. Your sacrifice will enable future missions. You've become part of the history of exploration, a name that will be remembered alongside Magellan, Shackleton, Armstrong, and all the others who pushed the boundaries of human knowledge. Is this a noble end? Or is it tragedy? Perhaps it's both. The exploration of space has always involved risk. The Apollo astronauts knew they might not return. The Space Shuttle astronauts knew the risks every time they launched. Future explorers of Europa, whether human or robotic, will face dangers we can barely imagine. But the drive to explore, to discover, to understand seems to be fundamental to human nature. We can't help but wonder what's over the next hill, across the ocean, on the next world. Europa calls to us precisely because it's so alien, so mysterious, so potentially full of secrets. What mysteries remain? Even if we send missions to Europa, even if we manage to explore its ocean, there will still be unknowns. The ocean is vast. We couldn't possibly explore all of it, not for centuries at least. There could be regions we never reach, phenomena we never observe. The ocean floor might have features we never discover. If life exists, there could be species we never encounter. And there are deeper mysteries too. How exactly did the ocean form? Has it existed continuously for 4.5 billion years, or has it frozen and melted repeatedly? What exactly is the ice shell structure? Are there currents in the ocean? And if so, what drives them without wind or temperature differences from sunlight? What is the exact chemical composition of the ocean, and how has it changed over time? Some mysteries might be unsolvable with current technology. We might need breakthrough innovations in power generation, propulsion, material science, and robotics before we can truly explore Europa properly. By the time we have that technology, decades or even centuries might have passed. The scientists and dreamers who first conceived of exploring Europa will be long gone, but their legacy will live on in the missions that eventually reach that distant ocean. Here's a question for you to consider. If we discovered life on Europa tomorrow, how would it change your life? Would you think about your place in the universe differently? Would it affect your beliefs, your values, your priorities? For some people, it might be the most important discovery imaginable. For others, it might be interesting but not personally relevant. Human psychology is strange. We can hear about discoveries of new particles, new galaxies, new phenomena, and they barely register. But something about life, about biology, about the possibility of other living things in the universe, touches us more deeply. Perhaps it's because we recognize ourselves in life, even alien life. We're alive, and so the question of whether other things are alive feels personal in a way that physics or chemistry doesn't. If you could ask Europa's ocean one question and get an answer, what would you ask? Are you alive? How were you formed? What secrets do you hold? The ocean can't answer, of course. It's a body of water, not a conscious entity. But in a sense, the ocean does hold answers. They're written in its chemistry, its currents, its sediments, its possible biology. We just need to learn how to read them. That's what science is. Learning to ask nature questions in ways that nature can answer. An experiment is a question. A measurement is a question. And nature answers through the data we collect, the patterns we observe, the laws we discover. Europa has been answering questions for 4 centuries, ever since Galileo first saw it through his telescope. With every new observation, every new mission, every new measurement, we learn more. The Voyager spacecraft that flew past in the 1970s provided the first close-up images. The Galileo orbiter in the 90s and 2000s revolutionized our understanding, revealing the ice shell's complexity and providing evidence for the subsurface ocean. The Hubble Space Telescope has observed what might be plumes of water erupting from Europa's surface, geysers that could give us samples of the ocean without having to drill through the ice. Future missions will continue this tradition, each one answering some questions and raising new ones. There's something poetic about Europa. It's named after a figure from Greek mythology, a Phoenician princess who was abducted by Zeus in the form of a bull and carried across the sea to Crete. The moon Europa, too, is associated with water, with hidden depths, with mysteries. The Greeks couldn't have known about the icy moon when they told the story of Princess Europa, but the name fits nonetheless. Both the mythological Europa and the astronomical Europa are connected to journeys across water, to secrets, to divine or cosmic forces beyond human control. And what of Jupiter itself, looming in Europa's sky? Jupiter is named after the king of the Roman gods, equivalent to the Greek Zeus. The planet is a monster, 318 times Earth's mass, massive enough that it almost became a star. If Jupiter had been about 80 times more massive, nuclear fusion would have ignited in its core, and our solar system would be a binary star system. Europa orbits this failed star, bathed in its radiation, squeezed and heated by its gravity. In a sense, Jupiter is both Europa's tormentor and its life-giver. Without Jupiter's tidal forces, Europa would be a frozen, dead ball of ice all the way through. The ocean exists because of Jupiter, even as Jupiter's radiation sterilizes the surface. It's a complex relationship, violent, and creative at once. If you were on Europa's surface, watching Jupiter move across the sky, what would you feel? The planet would be enormous, more than 11 times wider than Earth, appearing as a sphere nearly 47 degrees across in the sky. For comparison, our moon appears about half a degree across from Earth. Jupiter would fill a huge portion of Europa's sky, and you'd be able to see incredible detail. The bands of clouds, the great red spot, the storms and swirls. You'd also see the other Galilean moons passing in front of or behind Jupiter. Io with its yellow and orange surface colored by sulfur and volcanic activity, Ganymede, the largest moon in the solar system, and Callisto, ancient and heavily cratered. This would be a sky unlike anything you can see from Earth. A sky that would make you feel simultaneously insignificant and connected to something vast. But you wouldn't be on the surface, not unless you had extraordinary protection from the radiation. You'd be inside a shelter, buried under meters of ice to shield you from the particle bombardment. Or you'd be deep in the ocean, where the ice and water above provide natural shielding. The radiation on the surface is one of the greatest challenges for any future mission. Electronics can be hardened against radiation, but there are limits. Prolonged exposure would eventually degrade any system. Humans would need even more protection. The radiation environment is so harsh that it's one of the reasons most mission concepts focus on the ocean, where you'd be shielded naturally. Let's consider once more what it would really be like to fall into Europa's ocean, but this time think about the emotional and psychological journey. You'd begin with anticipation and probably fear, descending through the ice not knowing what you'd find. Then the breakthrough into the ocean, the moment of transition from solid to liquid, would bring a surge of adrenaline. As you descend into the water, the initial fear might give way to awe. You're in a place no one has ever been, seeing things no one has ever seen. Every moment is a first. As you go deeper, the enormity of the ocean would start to weigh on you psychologically as surely as the pressure weighs on your vessel physically. The darkness, the isolation, the alien nature of it all would test your sanity. If you encountered potential life, you'd feel excitement, wonder, perhaps a kind of kinship even with something utterly alien. You're both alive, both products of the same universe, even if you evolved on different worlds. But there might also be unease. What if the life is disturbing in its alienness? What if it behaves in ways that violate your expectations, your sense of how living things should be? On Earth, all life shares certain characteristics. It reproduces, it metabolizes, it responds to stimuli, it maintains homeostasis. Europan life might do some of these things very differently, or might have characteristics we don't recognize as biological at all. And finally, if your mission is one way, you'd face the reality of your mortality in the most profound way possible. You'd die alone in an alien ocean, farther from home than any human has ever been. Your body would remain on Europa, a permanent monument or perhaps eventually a part of Europa itself, your atoms mixing with the ocean and becoming part of the alien ecosystem if one exists. There's something both terrifying and beautiful about that. In a sense, you'd become part of Europa, a human contribution to an alien world. Would anyone volunteer for such a mission? History suggests they would. People have always been willing to risk everything for discovery, for knowledge, for the chance to be part of something greater than themselves. The first humans to reach Europa, whether they survived the journey or not, will be remembered for as long as human civilization exists. Their names will be taught in schools, their faces will be in history books, their story will be told and retold. For some people, that kind of immortality is worth any price. But let's hope we can do it differently. Let's hope that technology advances to the point where we can explore Europa and return safely. Let's hope that we can send sophisticated robots first, robots that can swim through the ocean, sample the water, image potential life forms, and send back all that data without risking human lives. Then, perhaps, when we understand Europa better, when we know what we're dealing with, humans can follow. We could establish a base on Europa, perhaps on the surface or even within the ice, using the ice itself as radiation shielding. From that base, we could send submarines into the ocean, explore thoroughly, and study any life we find. This is probably decades away at best, more likely a century or more. The challenges are immense, but they're not insurmountable. Humans have overcome seemingly impossible challenges before. We've split the atom, walked on the moon, eradicated diseases, built machines that can think. We can figure out how to safely explore Europa. It will take time, resources, international cooperation, and brilliant minds working together. But it can be done. And when it is done, when we finally have detailed maps of Europa's ocean, when we've cataloged its chemistry and perhaps its biology, when we understand this alien world as well as we understand Earth's oceans, what then? Europa is just one world. The solar system has other ocean worlds. Enceladus, a moon of Saturn, which also has a subsurface ocean and active plumes. Titan, also orbiting Saturn, which has liquid methane lakes on its surface and possibly a water ocean deep underground. Ganymede, which also likely has a subsurface ocean. Even distant Pluto might have liquid water deep inside. Beyond our solar system, there are exoplanets, thousands of them discovered so far, and some of them might be ocean worlds. The universe might be full of worlds with liquid water, with chemistry, with the potential for life. Europa is our nearest opportunity to test the hypothesis that life is common. It's close enough that we can reach it with current or near-future technology. It has conditions that seem potentially habitable. It's large enough and active enough to be interesting. It's the perfect target for our first serious attempt to find life beyond Earth. Not Mars, which is closer but probably dead and dry today. Not Venus, which is a hellscape of heat and acid. Europa, with its hidden ocean, is the best bet. Imagine the day we confirm life on Europa. Imagine watching the news conference where scientists announce the discovery. They'd show images, chemical data, perhaps even video of organisms moving in the water. The world would stop to watch. It would be bigger than the moon landing, bigger than any scientific discovery in history. Stock markets might fluctuate wildly as investors try to figure out what it means. Religions would have to grapple with the theological implications. Philosophers would debate what it means for humanity's place in the cosmos. And ordinary people would look up at the night sky and know, truly know, that we're not alone. Or imagine the opposite. Imagine we explore Europa thoroughly and find nothing. No life, no organic molecules, no chemistry that suggests anything biological. The ocean is sterile, a vast dead sea under the ice. What would that tell us? It might mean that life is rarer than we hoped, that Earth is unusual or even unique. It might mean that our theories about what life needs are wrong, that liquid water isn't enough. Or it might just mean that Europa, specifically, doesn't have life, but other worlds might. The absence of evidence isn't evidence of absence, as the saying goes. Even if Europa is sterile, there are still many other places to look. The search for life is, in many ways, a search for ourselves. We want to understand where we came from, why we're here, what it means to be alive. Finding life elsewhere would give us perspective. It would show us that life isn't a miracle that happened only once, but a natural process that occurs when conditions are right. It would suggest that the universe is fundamentally hospitable to life, that the laws of physics and chemistry that govern the cosmos are biased toward complexity, organization, and biology. That would be a profound insight into the nature of reality itself. Conversely, if we search extensively and find nothing, if we explore Europa and Enceladus and Mars and Titan and find only sterile rock and water, it would suggest that life is rare, that Earth is precious, that we should cherish and protect our biosphere because it might be the only one in a vast, empty universe. Either finding has value. Either way, we learn something fundamental. As you float in Europa's ocean, in these final moments, maybe that's what you think about. Not the specifics of your situation, not the mechanics of your dying vessel, but the larger meaning. You're part of the search. You're part of humanity's effort to understand the cosmos. Whether you find life or don't, whether you survive or don't, you've contributed. Your data will inform future missions. Your experience, however brief, has added to human knowledge. In some small but real way, you've moved the species forward. And then, the end comes. The pressure wins. The water claims you. Your consciousness, that strange property of organized matter that allows you to think and feel and wonder, dissipates. The atoms that made up your body remain, mixing with the ocean, becoming part of Europa's story. In 1 billion years, long after human civilization has either spread across the galaxy or disappeared entirely, those atoms will still be there, cycling through Europa's ocean, perhaps incorporated into living organisms if life arises or is seeded there, or perhaps just part of the ocean's chemistry. You become part of something larger, something ancient and ongoing.